Hello and welcome. Today we're going to move on to a new chapter on functions of a complex variable. And so in this section we're going to talk about, so let's just reactivate our understanding of functions. So in the real numbers, right, we have some f of x is equal to y, and of course you put in a real number and then you get out a real number, okay? And so that is pretty straightforward. And the only real restriction is that it has to be unique. We can't have multiple y values for a single x value. As long as every single x value is associated with only one y value, then we have a function. And we can, of course, talk about and study all the functions. And a big part of the study of mathematics is the study of functions. And in calculus itself is really the study of functions. It's how we describe functions and their properties using derivatives and integrals and things like that. And so, at least at the basic level, that's what calculus is. Of course, the study of functions goes well beyond calculus, but calculus is a set of descriptive tools to help us study functions. Okay, so now let's go on to the complex plane. Okay, so with the complex plane, we now have something like this. F of z is equal to w, okay, where z and w are elements of the complex plane. All right, and so we want to now just get some basic ideas of what this is. So first of all, we know that we'll say z is equal to x plus I y, and we've commonly thought of complex numbers as essentially vectors. And of course, w we're going to call u plus iv, and that's also these are two vectors. So we can think of this really as a vector function, and we can think of it as r2 to r2. Although we'll see that when we allow for complex arithmetic to occur, we have really interesting ways of studying what kind of functions happen when we think of these vectors as complex numbers. And that is the essence of what we'll do in this class. But right now, let's think of this as a vector function and see what we can do with it. All right, so we can write this as follows then. So this is actually, I can put this as f of z, but I could actually write this as actually f of x comma y. And rather than writing this as w, we're going to write it as u plus iv, right? So we have two inputs and two outputs. And we can think of this as actually u of x comma y plus iv x comma y. So now we have these two functions, right, that are a function of both x and y. All right, and that's now the essence of what we'll do. So let's talk about an example. Let's talk about f of z is equal to z squared. All right, so we can write that as x plus iy times itself, right? And that's going to be equal to, now we have to do all the arithmetic here, the complex arithmetic, so we have an x squared. And then when I multiply iy times iy, I get a minus y squared. And then also a plus I 2xy from the two cross terms that get multiplied out. And we can see clearly that this is our u function right here, and our I, and then this would be our v function of x comma y, v x comma y. Okay, so that now we see an example of how this works out. So a lot of what we'll be doing in this class is identifying the real and complex parts of functions, and then trying to understand some of their examples. So let's go through another example real quick. So let's talk about f of z is equal to the squared complex modulus of z. All right, so this is actually z times z bar, which is x plus iy. So this is another example. X minus iy, which is equal to x squared plus y squared. But here, the two cross terms cancel, and we're left with I, 0. So in this case, we have u of x comma y is equal to x squared plus y squared, and v x comma y is just equal to 0. Okay, so that's an example where this function is actually real valued. Okay, so now what we want to talk about is mappings. All right, so we can always think of functions as sort of a mapping of one thing onto another. So for instance, if I had a complex plane, I have some set in this plane, and I have some function, so this is y and that's x, that's our imaginary axis, right? We can take of that set, f of s, then, as being mapped down and turns into something else, We'll call that f of s, right? All right, and we want to talk about, and then what happens between these two sets. And this is this relationship between these two sets. And this is now in the VU plane, right? With this sort of scenario, we want to now study some basic ideas we can using this sort of understanding of what a function does. So this is more set-oriented viewpoint on functions. Okay, so we're thinking more in terms of set theory here. Okay, so for instance, in this particular example up here, I take a set out here, and if I'm going to map it through f of z is equal to the complex modulus squared, the mapping is completely going to be the positive real line. I can just kind of write it like that. So in this particular case, because S contains none of no complex number that is near the origin, we know that actually, I have to go doing a little erasing here, that it's really like this, right? So this is a bounded set, so we should be able to, it should look something like this, where every complex number z inside this set is all within a particular modulus, so it should look something like that. All right, so and that's the idea. So let's talk about some other mappings. So some basic ideas of mappings. So we have, hold on, sorry. We'll go on to the next page. All right, so let's think now about some of these mappings. So we have, if we have some set, and then we have some function, and it goes somewhere else, we often type of f of s, this new set, we like to call it the image of s under, or I should say, from or by f. Okay. So the set f of s is the image of s on the from the action of f. All right. Then we can also talk about the inverse image, and I'm going to call that f inverse s. And that's not necessarily just s. It could contain other things. So sometimes they call that the image of. Oh, sorry. I'll take away that notation. So it could contain other things here. And what the idea here is, this is the set. It's the set of all u comma v points that have, oh sorry, I am really getting tripped up here today. It's the set of all points in the xy plane that have f of s as the image. Okay, so if there could be a point here that does get mapped to here. So S, of course, point there does go to somewhere over here. We've established that. But other points here could also go to the same point. And that we know, if I have z here, and this is f of z, and that's equal to w, we could have z1 and z2 both going to the same w. What's not allowed, though, multiple w values are not allowed. Otherwise, it wouldn't be a function. So we can have many z values going to the same w value, but not the other way around. We can't have one z value create more than one w value. So for instance, let's think about it. Let's think about this function. Let's think about f of z is equal to z to the 1/2. So if I write this down, it's still sort of unclear which of the two roots we want. So we need a little clarification here, and in general, if we have multiple valued functions, we need to specify which of the values that we want, and that's going to have to be done, on a case-by-case basis, depending on the function itself. So, for instance, we can write this as z. We can write in polar form as e to the I theta to the 1/2. We know that we can also write this as r e to the I theta plus 2 pi k for every value of k, and then we 1/2, and that's going to be all over 2. But we can say that we're going to say set k equal 0. All right, and that's saying basically we're going to take the principal value. Or take the principal argument of z to be equal to theta. And what we're saying then is that now, so better is to say f of z is equal to r e to the I capital, the principal argument of z, all to the 1/2 power. Or we can write this another way as, or r to the 1/2 e to the I theta over 2, where theta then is between pi and negative pi. All right, and that, of course, is the principal argument. So those are now better ways to write this function. So now it is a function that is not multiple valued. Okay. All right. So now let's talk about some simple mappings, some basic mappings. Okay, some basic mappings. For instance, translation. We're going to talk about translation, rotation, and also reflection. Okay, so let's talk about this one, translation. So for instance, if I have a point, and all points z get mapped to z plus some other number, some other complex number. And what that does then is any set, I talk about a set, and it's just going to move that set over. And any other set, if I talk about this set here, it just moves it over to there. So that would be a translation. So for example, let's talk about this example of z plus 3 plus I. Okay, I'm going to say that's my function. All right, so now what I want to do then is say, okay, so what does that look like? So I'm going to take the neighborhood around 0 with a 1 radius, okay? And I want to find out where that gets mapped to. I want to find f of n 0, 1, and that's pretty straightforward. So here's my neighborhood. It's just this disk, radius 1, and that's going to get mapped to the point 1, 2, 3, and then go up 1. So here was the old set right here, and the new set then is there. So that is right there, f of s, or f of n 0, 1. Okay, right, so just a movement in the plane, okay? A translation. It's a translation that's true for every point in the plane. Okay, so now let's talk about other ones. So let's talk about that one of the rotation. Okay, so we can, and we might talk about z equals 0. All right, so here would be a simple example of a rotation. So let's say by angle gamma. So f of z then can be z times e to the I gamma. All right, so that should cause a rotation. We can see this as if we write z in polar form, r e to the I theta times e to the I gamma, and that becomes a rotation of the complex plane, e to the I theta plus gamma. Okay, so let's just get an idea of what this does. All right, so now let's talk about, so then if I have some set, if I have some point there as a theta, then if I have some gamma, if I want to rotate that point a little ways, it could be that my gamma is there, and my new point is there. So that's z, and this would be f of z right there. So that would be the rotation. So for example, we can talk about maybe gamma is equal to pi, and we're going to take the set will be we'll talk about it being 2 1. So I'll write my complex plane that way. So I go out 1, 2, and I have the set like this. That's my neighborhood around the point 2. Okay, and now I'm going to rotate it by pi. So what would we do? That's 180 degrees. We move it around to 1, -2, and my new set is there. So that would be a rotation in the plane. But what about rotation about z naught, which is not equal to 0? What about that kind of thing? So let's see if we can think of that. So the idea here is then we have some point z naught, and I want every point with respect to it to be rotated by some gamma angle. All right, and that means the whole plane is now going to rotate around that point. All right, by an angle gamma. So let's see if we can write such a function. So f of x, or f of z, sorry, is equal to z, but I want to do something to z. I want to rotate it, but first what I have to do is take anything related to that point. So z itself is the only point that nothing happens to it. So just like with the rotation in the plane, 0 is the point where nothing actually rotated. So what we need to do is subtract z naught from that, and that essentially moves everything in the plane. That's a translation down to 0. And then what we want to do then is e to the I gamma, and that rotates everything, right? So we move everything down. So I take this point out here, and then it gets moved down to here. And then it gets rotated. It gets rotated around by gamma, right? And now what do I need to do is then I need to go plus z naught to bring it back. So that causes that rotation around. Okay, so that would be a rotation around the point z naught. Okay. All right, so now finally what we're going to talk about briefly is reflections. So let's talk about reflections. So we'll just talk about two examples of a reflection, and that is f of z is equal to z bar, or rather the complex conjugate x minus iy. And that's a reflection about the real axis. So if here's my point x plus iy, the function then takes every point and flips it to x minus iy. So that would be a nice reflection transformation, or a reflection mapping. So if you have a neighborhood up there, it's going to move the neighborhood down there. Okay, so that's a reflection about the x-axis, or the real axis. But what about imaginary axis? Well, that's pretty straightforward. F of z is equal to negative x plus iy. And that'll take a point here, x plus iy, and then make it go across there to minus x plus iy. Okay, and so any set over here then would get magically put over there. So s, f of s. Sorry, I'm trying to make the sets look the same. Okay, so that's the idea. Okay. All right, so finally, let's just go over briefly some examples. One example of a function and how a more complicated example works. So I'm going to erase this. I'm running out of layers. Okay, so we'll talk about the function. We'll go back to the original function we studied at the very beginning, z squared, which we know was equal to x squared minus y squared plus I to xy. So what does the mapping of this function look like in the complex plane? What happens to sets in this complex plane? So this turns out to be pretty interesting. So what we're going to do is be looking at level sets. Okay, so let's say I want to find, so I'm going to find out what's going to happen. What if x squared minus y squared is equal to c1, where that's greater than 0? Okay, and we'll just assume this. Now if, right, so if we pick an x and a y in our plane, to have this property, what does that look like? Well, that means that y squared is equal to x squared minus c1. That turns into y is equal to plus or minus square root of x squared minus c1. So obviously the allowable xy combinations then, so if I at the point square root c1 plus, and there's also a minus version, minus square root c1, we see that the point that we see that it's at 0, right at that point. But then it goes up and it looks like a square root function that goes up like that. And also there's a negative branch to it because we have a positive and a negative, like that. And then we have another one going off that way. So this is a hyperbola. All right, so any hyperbola in the complex xy plane gets mapped to a constant line, right? So here's my f function. I'm going to take any one of these hyperbolas now, gets mapped over to the uv plane to be, so u then is just going to be c1. So it's going to be any vertical line. So I'm going to try to draw this as accurately as possible. So that is c1. And we can see that if I were to write this in another way, so if this is equal to y, that means then that this function then I can write as x times square root plus or minus, so that'll be x squared minus c1 times 2, and that's equal to v. So the v will change as follows. So if I find a point on here, it's going to be a point there, and if I go back and forth across this, it's going to go up and down on this line here. Okay? And then for every c1 value here, if I pick a different hyperbola, like that, say, it's going to create a different line here. So each vertical line then, so each hyperbola here goes to a different line. And so on and so forth like that. Okay, so that's just an example. So if I pick a point, and every point on this hyperbola goes to a vertical line, and that just tells you something about the mapping in the complex plane of this more complicated function. So clearly, this is a really rich and pretty difficult to visualize what's going on here. It takes a little bit of analysis. It takes a little bit of algebra. And we'll find a lot of times to visualize mappings in the complex plane, it takes quite a bit of work to get an idea, and it's never quite easy where it just jumps out at you exactly what's happening to sets in the complex plane. So I hope that helps get you some insight in terms of what work has to be done to analyze functions in the complex plane and where sets of things are. So in this case, we see that. Let's try to get some examples going here. So for instance, if my set is just this hyperbola related to C1, that is going to clearly map onto this vertical line here. What about the inverse image? If that's my set S, what is this coming back? Well, we can clearly see that the inverse image contains both this right branch hyperbola but also the left branch on this other side here. So the inverse image are not the same. In fact, this function is not invertible, and we already knew that. Even f of x squared is f of x equals x squared is not an invertible function, and neither is a z squared. It's neither an inverse. It doesn't have an inverses either. So I hope that gives you some example of these things and how they work. All right, thank you very much.